So hi everyone, welcome to an exciting episode of QEA Videos. My name is Mark and I'm joined today by a special guest, Sung, who's here.
Yep, honored to be here.
So we're going to talk today about stuff that relates to complex impedance. This was something that came up in class, and a brilliant suggestion was made that rather than continuing to flail on the board, that we actually make a video to try to compress it a little bit and maybe flail a little bit less. So what I want to do in this video is actually try to explain the idea of complex impedance and help you to understand what the complex number part means of complex impedance. Okay, does that sound like a plan?
Mm-hmm.
Good with that? Okay. All right, so let's actually start by sort of thinking about what the conditions are and when it actually makes sense to use complex impedance. So when does it make sense? So Sung, what's your sense of when it actually makes sense to use complex impedance?
Well, based on the little exposure that I had in class, it seems like complex impedance makes calculation easier.
Yeah, it makes calculation easier, but it makes calculation easier in a very specific situation, right? When you're actually driving or what initially seems like a very specific situation, when you're driving the circuit with a sinusoidal signal, then it's sort of easy to use complex impedance and complex voltages and so on because of the fact that that complex numbers are an easy way to represent sinusoidal signals. Okay, so the sort of one of our sort of key assumptions here is that we're driving things with a sinusoid. Okay, and what I want to do first is just drive a couple of sort of simple things with a sinusoid and think about what actually happens when we do that. So here's the first thing we're going to do. We've got a sinusoidal voltage source, right? So if I wrote this voltage in sort of real terms, I would say this is like V naught times cosine omega t, right? If I wanted to write that in complex, as a complex voltage, I would just write V naught times e to the j omega t, right? Which is actually, notice that this is simply the real part of that, okay? And what I'm going to drive with that oscillating voltage, that sinusoidal voltage, is just a resistor, right? So there's the circuit that we're dealing with. Okay? And what I want to think about is what's actually going on in this circuit. What's the voltage across that resistor? What's the current through that resistor? And the voltage is pretty easy to think about, right? We can actually plot what the voltage is right away, right? It's the real part of V naught times e to the j omega t. So it's got a magnitude of V naught. It starts out at plus V naught, goes down, goes back up, right? It just sinusoidally varies.
Yep.
That sound cool? Okay. What's I going to be in this particular circuit?
I is a sine part of this Euler's formula thing, right?
Well, okay, so there are two i's running around. One is I like
the
square root of -1,
Okay,
which I'm referring to as J. This is why electrical engineers always use J, because I is current, and so J is the square root of -1. I'm actually talking about what the current in the circuit is. Right, and the current in the circuit, well, I've got a resistor here, and I've got a voltage drop of V naught cosine omega t, or V naught e to the j omega t. So what's the current going to be through that resistor?
So it'll be V naught over R.
So if I would just do it in real terms, I'd write V naught times cosine of omega t divided by R. Or if I wanted to write a sort of complex current, right, this is sort of my complex voltage, I would say that it was simply V naught over R times e to the j omega t.
So is complex current same as the real current?
So all the complex current is a way of representing the real current more compactly, right? Like physically, what we're interested in here in time is what is the real part
Just
of this,
the real
right?
part.
So if I said what's I physical, right? I physical is the real part of I complex, right? In the same way that V physical is the real part of V complex. Okay?
Yeah.
So if I actually ask what's the physical current in this circuit, well, it's the real part of V naught over R e to the j omega t. In other words, it's V naught over R times cosine omega t. And so the actual current in this circuit will just be proportional to what the voltage is, right? And this value here of the current will be V naught divided by R. Okay? So if I go I'm just going to go one step further in this to say what the way that I think about what impedance is. Impedance is the ratio for a given circuit element of the voltage to the current. So what's the impedance for this resistor?
It'll be just resistance value.
Yeah, if I take my complex voltage and divide it by my complex current, right? So I get, let me move this up a little bit. So my impedance of the resistor, right, is V naught e to the j omega t, right, divided by I times e to the j omega t, or I naught times e to the j omega t, but of course I is simply V naught over R, right? So I end up simply getting R, right? So the impedance of a resistor is just R. Okay, sound good?
Yep.
All right, so let's do a second circuit element. Okay, so now instead of talking about a resistor, we're going to talk about a capacitor, right? So again, we're going to drive this thing with a complex voltage, right, which is just a way of representing the real voltage. So my driving voltage is V naught e to the j omega t, okay? And I've got that hooked up to a capacitor that has a capacitance value of C, okay?
Yeah.
So now the voltage across this capacitor is simply V naught j omega t, right? But what's the current that's flowing in this circuit?
Well, that's the formula for capacitors. I equals C times dV over dt. And
Right, so
use
the
that.
current flowing into a capacitor tells you how fast the voltage across the capacitor is changing, right? If I have a lot of current flowing in, then I'm building up more and more and more charge here. It's getting more and more positive voltage, right? If I have current flowing out, the voltage is dropping over time. So you're exactly right. The current into or out of a capacitor is actually the capacitance times dV by dt, right? And notice that a bigger capacitor, right, something that holds more charge, gives you more current for a given rate of change of voltage, right? So that kind of makes sense, right? A big capacitor, you could have change the voltage just a little bit and you get a lot of current out of it in the process.
Bigger bucket, basically.
Bigger bucket, exactly. Okay, so now if I take this and plug it in, right, I can actually figure out what my complex current is, right? What's my complex current going to be?
So where are you plugging this?
So I'm going to
I
say
into?
I complex, right, is equal to C times dV complex
Okay.
over dt, right? Well, what is V complex? It's V naught times e to the j omega t,
Yeah.
okay? So what is I complex going to be then?
Are we just simplifying
I'm
this
just
expression?
taking a derivative,
Okay.
right? So what depends on time in here is just the exponential that depends on time. When I take the derivative of a times t, of the exponential of a times t, I pull down an a, right? So what am I going to pull down
So
here?
it'll be J
Pull down
omega.
j times omega, right? So I get j times omega times c times v naught e to the j omega t, okay? Now, that's kind of weird looking, right? Because now we've got this complex current which actually has a j out in front of it,
Yeah.
right? So that's a little strange to think about, but we can think about it a couple of ways. One way to think about it is actually, let's go back to the actual physical current, right? So what is I physical? Well, I physical is the real part of I complex, right? In the same way that V physical is the real part of V complex, right? So what's the real part of this? Well, I've got J times omega times C, and then I'll use Euler's formula just to sort of write this out. V naught times cosine omega t plus J times V naught times sine of omega t, right? So when I multiply this out, what do I get? Well, I get a J times cosine omega t. The first term is actually imaginary,
Oh.
right?
Yeah.
The second term, I get J times J. I get a negative omega times C times V naught. So let me make sure I'm actually getting this written down in a way that times the sine of omega times t. Okay, you buy it?
Yep. So that becomes a real part.
Right, this is actually what the physical current is. The physical current is the real part of that complex current, okay? So if I actually plot that and think about it, right, my voltage, right, is again doing this, right? But my current is not following the voltage anymore. My current actually starts out as a negative sinusoid, right? So it's actually 0 here, right? It's at its largest negative value at that point, right? Goes back to 0 here, right? Is at its largest positive value at this point, right? And in fact, you can see the current actually is leading the voltage, or the voltage is lagging the current by a time that's basically pi over 2, or you need to take into account what the omega value is, but this phase difference is pi over 2, right? And this sort of makes sense. You can see here I've got a negative current. Since I've got a negative current, that means I've got current flowing out of the capacitor. Since current is flowing out of the capacitor, the voltage of the capacitor is dropping, right? At this point, I start to have a positive current, right? Positive current means the voltage on the capacitor is increasing because I've got current flowing in, right? So that's one way to sort of interpret this j omega c, right? Another way to interpret it that's a little bit more sophisticated is to rewrite that j as an exponential, right? So I could actually rewrite I complex as being omega times c times e to the, well, how do I write j as an exponential? I propose that j is equal to e to the j pi over 2.
Is it?
Okay? Well, let's see if it is. What's the magnitude of j?
Square root of
So the square root of 1
1
has a length of 1,
yeah.
right? I mean, so if we actually plot j on the complex plane, right, it's got 1 along the imaginary axis and 0 along the real axis. In other words, it has a magnitude of 1 and an angle of pi over 2,
Yeah.
right? So I could just rewrite j as e to the I, e to the j pi over 2, right? So now I've got omega times c times e to the j pi over e to the j pi over 2, and times e to the j omega t, and I forgot a v naught out here, right? Or in other words, it's omega times c times v naught times e to the j omega t plus pi over 2. Okay, so another way I could write my real current, right? So my real current would be the real part of this, right? Real part of this is going to be omega times c times v naught times the cosine of omega t plus pi over 2. Right? And of course, the cosine of something plus pi over 2 is the same thing as negative the sine. The reason this is a little bit better way to write it is that it actually embeds, you can actually see that this stuff out front, right, embeds two pieces of information. One is what the size of the current is relative to the voltage, and the other is what the phase of the current is relative to the voltage.
Yep.
Okay? So if we now take this one step further and we say, okay, well, what does that mean about the impedance of a capacitor? Well, the impedance, we said, was equal to the ratio of the complex voltage over the complex current, right? Well, my complex voltage, we know, is V naught e to the j omega t, right?
Yep.
The complex current we just figured out, if I remind you, right, is j times omega times c times v naught e to the j omega t, right? So we've got j times omega times c times v naught times e to the j omega t, right? In other words, my complex impedance is 1 over j omega c, right? Because all this cancels out, all that cancels out, okay? So what does that actually mean, that it's 1 over j omega c? Well, one of the things that a different way I could write that is to write this 1 over j as a phase, right? So I could also write this as 1 over omega c times e to the minus j pi over 2, right? Because 1 over j is negative j is e to the minus j pi over 2.
Yeah.
Okay, so what this actually tells me is that the voltage is going to lag the current by a phase of pi over 2, right? When I have an impedance that has a negative phase, that tells me the voltage is lagging the current, right? And it also tells me that the size of the voltage is proportional to the size of the current with a proportionality constant of 1 over omega c, right? So that means that for really large frequencies, what's going to happen here?
Can you remind me what omega stands for? in
Omega
this?
is the angular frequency.
Angular frequency.
So omega is 2 pi times the frequency in hertz, right? It's in radians per second. And it's basically how fast the sinusoid is going up and down,
Okay.
right? So like if you're singing a low note, omega is small, right? So if I go, oh, that's an omega that's probably on the order of, I don't know, maybe that's 300 hertz or something, so on the order of 2 pi times 300 hertz. And if I sing really high, which I'm not going to do, right? I'm just not going to sing.
Okay.
Okay, you get a higher omega value. So for high frequencies, in other words, if you're driving this circuit with a really fast sinusoid, right? What that means is that the impedance of this is very small,
Yeah.
right? Because omega is large, so the impedance is small. Since the impedance is small, the ratio of the voltage to the current, right,
It's also small.
is also small. In other words, I have a really big current for a given voltage, right? So a capacitor acts like a short at high frequencies, right? So Z actually goes to 0 for high frequencies. So as omega goes to infinity, right? And Z goes similarly to infinity, or actually minus J times infinity, right? And this is also minus J times 0, but as omega goes to 0, okay?
So you mentioned that this capacitor acts as a short in the circuit.
At high frequencies, it will act as a short.
So what does short mean in electrical engineering?
Okay, so what short means is that it's basically like it's just a wire.
Just a wire. So,
So
nothing's there.
if I have this circuit, right? Okay. At low frequencies, right? If I drive this at a small frequency, this circuit becomes approximately,
Just a resistor.
right? Because
Is it
at low
RD?
frequencies, the impedance goes to infinity. In other words, this becomes an open.
Open.
Right.
Okay. So this is a low frequency, what you just drove.
Right. For high frequencies, it turns into this. Whoop, sorry, we lost that. Right. So at low frequencies, this capacitor acts like an open, right? It basically doesn't, it's got a very high impedance, it doesn't allow current through it. And at high frequencies, this capacitor acts like a short, it basically acts like a wire.
Oh.
Okay? And that's why you can think about this as a low pass filter, right? For a low frequency,
Isn't it high
V
pass
out.
filter?
this is a low pass
Low
filter,
pass.
right? Because at low frequencies, the output voltage is basically the same as the input voltage,
Oh yeah, I see. Yeah.
right? At high frequencies, the output voltage is basically 0. Or at very high frequencies it goes to 0, but since it's a short here, all the voltage drop is across the resistor,
Okay.
right?
I'm not quite sure why this circuit, the small frequency circuit, has a voltage output that's same as the input.
Well, I can't have any current flowing in it,
Yeah.
right? Since there's no current, there's no voltage drop across the resistor.
Oh, okay.
Therefore, the voltage drop from here to here must be equal to the voltage drop from here to here.
Which is same.
Okay.
Okay.
All right. I'm going to stop this video here because it's already 18 minutes long.
Okay.
But we can talk about this some more on the next video if you feel so inclined.